Small molecule drug. Many of the small molecule drugs are from natural product. So here are some examples of a natural product. Paclitaxel, the famous Taxol anti-cancer drug, and salicylic acid, and hypochondrin B, the anti-cancer compound. So it looks like some of them is very complicated, and some of them looks quite simple. So hypochondrin case, the essential part can be remained, and then the other part can be removed to make a much simpler molecule, eribulin. Salicylic acid case, by adding acetyl group, reduced the problem of stomach and also increased the absorption. So two simple molecules, sometimes you can add up. Very complicated molecule, we can cut off. Paclitaxel's derivative, docetaxel, size is similar, but that improved the affinity to the target tubulin. Also, that improved the notorious solubility of paclitaxel. So similar size, but property was improved by chemical modification. Here is the very popular small molecule ibuprofen. And when you say the small molecule, the criteria is molecular weight is less than 500. That's what you call small molecule. And these kind of small molecules are mostly produced by chemical synthesis. When you look at the property of drug molecules, if you take the drug and then drug goes into the body and reaches the target, in this case, the COX-1 or 2 is the target of aspirin or ibuprofen. And if you block the function of this enzyme, now this effect we call pharmacodynamic effect. So pharmacodynamic effect or PD effect is how the drug affect our body. So that's pharmacodynamic properties. In contrast, pharmacokinetic property is how our body affect the drug. So when you take the drug and it goes into our body, and they can be distributed, and finally it should reach the target site. So the location is important. So this is what we call bioavailability, whether the drug molecule reaches the target, the site. So this case, the effect of a molecule itself is not important. Here we are focusing on whether the molecule is properly delivered to the right site. For more details, drug compounds is orally taken, then it should be absorbed first. So absorption is important. And then the drugs go into the liver and then they get metabolized and then distributed to the whole body, and whether it can reach to the target site or not, eventually that should be removed from the body. That is what we call excretion. So altogether, these are the four parameters, and me is the pharmacokinetic parameters. For convenience, sometimes we add T. Here, T is a toxicity. So altogether, we call this add MIT. And toxicity is not pharmacokinetic parameter. It's kind of a bad side effect, but that's also how the drug affect our body. So this is T is the pharmacodynamic property. In the drug development, if they analyze the reason why the drug development failed, 40% of them are pharmacokinetic problem issues, and 10% is animal toxicity, and 30% is efficacy issues. To systematically understand the pharmacokinetic property of drug molecules, Lipinski collected thousands of marketed drug compounds and analyzed the property. And he found some interesting trend. Drug compounds shows good absorption, means good bioavailability, when they have the following properties. First of all, the molecular weight of the molecule should be less than 500. And partition coefficient, the log value, is between 2 and 5, then that's a good property. If it is less than 2, the molecule is too hydrophilic. If it is above 5, that's too hydrophobic. Also, number of hydrogen bonding donors should be lower than 5, and hydrogen bond accept molecule should be less than 10. Also, rotational bond number should be less than 10. So these numbers somehow they have many fives in the rules. That's why this rule is called as Lipinski's rule of five. And these parameters are all pharmacokinetic parameters. That means whether the drug molecule can reach to the target site properly. Let's analyze ibuprofen as an example. Ibuprofen has molecular mass of 200, so this is less than 500. Log P value is around 4. This is also less than 5 and bigger than 2. How do we measure partition coefficient? For this, the drug molecule should be in water and organic solvent layer, and the standard solvent for organic layer is N-octanol. Here we measure the distribution of the molecule between organic layer and water layer. If this log P value is 0, that means the distribution between these two layers is 1 to 1. Log P value 2 means 1 in water and 100 in octanol. Still, that is considered as hydrophilic. Log P value is 5, that means 1 in water and 100,000 molecules in octanol. Above that, now we define that that molecule is too hydrophobic. Ibuprofen has one hydrogen bonding donor. So OH or NH, the proton source is considered as a hydrogen bonding donor in the case 1. Hydrogen bonding acceptor is oxygen or nitrogen atom, which can take the proton from outside. So those are the hydrogen bonding acceptor, in this case 2. Rotational bond, we can count here 1, 2, 3, 4, 5, 6, 7, 8. So rotational bond is also less than 10. So in that sense, ibuprofen is meet the criteria of Lipinski rule of 5. Let's practice with a little more complicated molecule, artemisinin and its derivative. Both molecules is less than 500, that's okay. The original artemisinin molecule is hydrophobic. That's why by adding hydrophilic motif like this, and then make the whole molecule's log P value as around 3. Hydrogen bonding donor number is okay. Acceptor is increased, but still the total number is less than 10. Rotational bond is also increased, but totally is less than 10. So the problem of original molecule's hydrophobicity was modified by adding new structure. So this is how we can modify the pharmacokinetic property of a molecule. Now let's move to the pharmacodynamic property. If the molecule has an activation effect, we call those molecules as agonist. So the measurement is activity. So here is agonist shows with the increased concentration, activity increase like this. If you measure inhibition of the target, then agonist will show with the increased concentration, inhibition is decreased. That means it is activated. If the molecule shows inhibition effect, we call those molecules as an antagonist. Then activity is decreased and inhibition effect is increased. So this is the opposite of an agonist effect. Activity of the compound can be measured in two different terms. One is the potency. In this example, compound A and B showed 100% the maximum value is similar, but required the concentration to reach its 50% effect is different. In this case, A is required much lower concentration than B to reach there. So that's why in this case we call compound A has a higher potency than B, or compound A is more potent than B. So in this case, the ED50 is defined by 50% the activity concentration. So this is A compound's ED50, and this is a B compound's ED50. Another activity measurement is efficacy. Sometimes the two compounds has a different maximum effect. In this case, compound A has a higher efficacy than B. So that most likely that implies that compound B is a partial agonist of A. So if you compare these two compounds in terms of potency, which compound is better? When you measure the ED50 values, A compound, it seems like they require lower concentration, so potency is higher for A. But when we measure the efficacy, B compounds has a higher effect than the A, so that means the potency and efficacy, not always the one compound is better than the other. Sometimes A compound is better in potency and the other compound has a better effect for efficacy.